Hello everyone, welcome back to the discussion on localization of mobile robots. So in the last lecture we briefly talked about Kalman filter based localization. So I explained about the logic of having a Kalman filter and then how this Kalman filter can be used for localizing the mobile robots. So as you can see here, so if you have the basic principle is that if you have two estimates, you can actually combine these two estimates or you can fuse these two estimates using a Kalman filter and get a better estimate. And the estimated, the new estimate will be having reduced covariance. That means the error will be much less than the two individual estimates that you had earlier. So that is the basic principle of Kalman filter. And we saw that there are some basic assumptions that the previous position and its covariance is known. For example, you know that the robot is at tk, the robot is at xk, and its deviation is standard deviation sigma is also known, and it's actually a white noise distribution, and it can be represented using this density function fx as 1 by sigma root 2 pi exponential of minus x minus mu square by 2 sigma square. So that is the way how we can represent this distribution, and that is the fundamental assumption that the error can be expressed using a distribution of this form. Now we assume that the robot is actually moving from here with the control input u and reaches the next position. So you will be having a prediction update because of u, that is a control input, and the predicted position can be given as xk tk plus 1, and then it will be having a deviation sigma k tk plus 1, and this can actually be calculated using the error propagation law we discussed earlier, because we know xk tk and then sigma k, and we know the control input and the covariance in the control input or the sensor inputs, and using these two we will be able to get the new. That is the first prediction update. And then from the prediction update we will be able to, so as you can see during the prediction update the uncertainty increases, and this uncertainty need to be controlled using a perception update. So in the perception update we use the sensors to get the information, and then we match the sensor data as well as the map data and use that one to calculate the Kalman gain, and then use the Kalman gain to get the new position estimate as well as its covariance. So that is basically the Kalman filter localization. So the steps involved in the Kalman filter localization, as I explained in the last class, I'll just go through once again. So go for the prediction update. Okay, so there are two updates, prediction and measurement updates. So we'll first go for the prediction updates. So that is the robot's position at time step t is predicted based on its location, old location t minus 1, and its movement due to the control input ut. So that is basically the prediction updates, and we saw that it can be done using the control input, if you know the kinematics of the robot, and using the error propagation law we will be able to get the new position, the prediction update position, which is xt hat, and pt, that is the covariance that can be obtained. Okay, and then the next step is the measurement updates. So what we'll do, we'll update this position, that is this position that it has already obtained using the control inputs. We'll try to update this using the measurement. So measurement is basically the perception update. You measure the surroundings, get some information, and then try to update it. That is basically measurement update. Okay, so we have two things in this. One is the observation using the sensors. So we call this as ZT, that is the sensor measurement ZT, and then we have the measurement prediction ZT hat. So we call this as the ZT hat. So this is ZT hat. So the prediction update is measurement prediction is basically what the robot is supposed to see from this position. If it is actually exactly at that position, what the robot is supposed to see based on the map information. So map has got some features, and if the robot is at that location, then as per the map it is supposed to see something, and that is this ZT hat, and this is the ZT, which is basically what the sensor is actually seeing. So, there are two things, one is what actually the robot is seeing and what the robot is supposed to see, that is the ZT and ZT hat. And as I mentioned, the predicted observations are what the robot expect to see, and it has to be expressed in sensor frame, because the map will be having its own frame, but all these features need to be transferred to the sensor frame. So, we use a transformation Hj to transfer all those images, all those objects what the robot is seeing as per the map, and then represent it as ZT, J, H. That is the prediction expressed in sensor frame. And now we will try to find out what is the difference between these two, what is the supposed to see and what it is actually seeing, and that is what we call it as the innovation VTIJ. Okay, so that is the matching stage. So, produce an assignment from the observation to the prediction, measure of difference between predicted and observed feature. So, you have a predicted feature and an observed feature. So, what is the difference between these two can be obtained using here ZTI minus ZT hat J, because there may be m objects the robot is seeing, there may be n objects what it is supposed to see. And now we need to match them, each one of these, and then find out the difference, which we call it as the innovation. So, if there is a map like this and the robot is actually, it is seeing an object here. Now, this is what actually the robot is seeing, I call this as Z1, and then the robot is actually supposed to see something here. So, I call this as Z1 hat. So, this is 1. Similarly, there will be 2, okay, then there may be 3 like that, 1, 2, 3, and some of them will be visible, some of them won't be visible. But the robot will not be knowing which one is what. So, it has to check with the one which is matching with 1 hat or 2 hat or 3 hat, it has to do the matching. So, it will do one by one, each one of these will be checked, and then it will try to find out which one is really matching, and based on this matching, it will use a validation gate to check whether it is the same object or not, because there is no point in comparing this object what they are supposed to see and then this object, okay, they are not the same. So, if the difference is within a validation gate, they define a small value, and if it is within that, then it will declare that okay, it is the same object what the robot is seeing and what the robot is supposed to see. Only thing, there is a small difference between the position what that is actually there and it is supposed to be there. So, that way it will try to use a validation gate, and then once it is validated, then it will try to how much is the difference, and that using that one it will try to find out an innovation covariance, which is given as Hj, Pt hat, Hj transpose and Rt I, where R is the sensor uncertainty and Pt is the covariance at the current position, and H is the Jacobian of this transformation J. So, that you will get a sigma innovation, or we call it as the innovation covariance. And once that is there, then we will get the new position xt as xt hat. Xt hat is the current position, and that plus kt Vt, or kt is the Kalman gain and Vt is the innovation. That is what you are getting, the total innovation that is calculated from all the objects, will be getting it as innovation. And then you have this kt, which is the Kalman gain, which can be written as Pt hat Ht sigma innovation inverse. So, that is basically the Kalman gain, and then the covariance of the new position, this the estimated new position will be somewhere here, and that will be something like this. That is obtained like this: Pt hat minus kt sigma innovation kt transpose. So, that is the way how we get the new position estimate, position as well as its covariance. So, this is basically the Kalman filter based localization of mobile robots. So, that is the basic principle. Okay, so once you have this, then it is xt is KTVT, and KT can be obtained as this is the Kalman gain. So, the best estimate of xt of the robot at stage t is equal to the best prediction of state at t, that is xt hat, before the new measurement zt, plus a correction term of an optimal weighing value kt, that is the Kalman gain, times the difference between ZT and ZT hat. So, that is basically the ZT and ZT hat are the predicted and the actual observations. The difference between that minus that is difference between that multiplied by the Kalman gain plus the previous estimate will be the new position estimate of the robot, and covariance is this one PT, because then again this PT will be the covariance at that estimated position, new position, and you can see it will be smaller than PT hat, because these are all positive. So, it will be always smaller than the previous covariance, that is the predicted covariance or the movement covariance due to the motion of the robot will be reduced to a new smaller value when we have a perception update. So, that is how we get the new estimated position. Okay, so I will take an example and try to explain this to you. Of course, we will not go through all the numerical stages, but I will explain the logic of how we do this. So, assume that we have a arena like this, what is shown here. So, this is an arena where a robot is moving. Okay, so there is a arena. Assume that the robot is at t minus 1, it is here. So, that is the position of the robots. So, that the blue circle what you are seeing is the robots, and you can see the two wheels also here, and it has got an axis here, the forward axis. So, at t minus 1 the robot position is we call it as xt minus 1, and we say that it has got a covariance of pt minus 1, which is represented using this ellipse. So, the ellipse basically tells that okay, this is the uncertainty of the position of the robot. The robot will be uncertain, it is still not sure what is its position. So, there is an uncertainty, but it is position is mean position is xt minus 1 and its covariance is pt minus 1. Now, the robot is getting a control input ut. So, it is getting a control input ut and then it moves to the new position here. So, that is the new position. Let me change the color to something. Okay. Okay, so this is the new position of the robot. So, after getting control input ut, the robot has moved to xt and it has estimated the position xt. So, we know that xt, that is the new position xt hat, is a function of xt minus 1 and ut. Okay, and that is the odometric. So, if you know if it is a differential robot, we know how to calculate the new position xt. So, xt hat can be obtained, and its pt, as we know that the pt, which is the covariance at this. So, this is xt minus 1 sorry x hat t, and there will be a covariance pt hat also. So, this pt hat again we know that it can be obtained as fx pt minus 1, fx pt minus 1, fx transpose plus fu q fu transpose. So, we can actually write this as q, where q is the covariance of the sensor used for measuring the travel, or it is the encoder uncertainty. So, we will be able to get this xt and pt, that is actually shown here. So, now we have a xt and pt. Now, what we need to do is to so if we really use a sensor, sorry, if you use the relationship for the differential robot, then we will get xt as like this. So, xt minus 1, yt minus 1, theta t minus 1. So, xt minus 1 will be xt minus 1, yt minus 1 and theta t minus 1 plus delta sr plus delta sl by 2 cos theta. So, this relationship we saw in the previous derivation. So, we will be getting xt like this, and then we will be getting the pt like this, and where qt, which is basically the sensor covariance kr delta sr and kl delta sr. So, that is what we get. So, from here to here we can actually do once we know the kinematics of the robot, and if you have the covariance of the sensor uncertainty is known, we will be able to calculate this. So, we will be getting the new position xt hat and the pt hat. So, that is what we do in the prediction updates. So, once that is done, the next one is the perception update. In perception update, what we need to do is to see what the robot is actually seeing from here. So, we will assume that there is a sensor attached to the robot, and the robot is using its sensor and using that to collect all the information from the surroundings. So, if it is a laser sensor, we assume that the laser sensor will be able to identify this wall, this wall, this wall and this wall. So, all these walls it will be able to identify using the sensor. So, that is what actually the robot will be getting as an information ZT. So, ZT will be what the robot is seeing using its sensor. So, it will say that okay, from my position, current position here, I am able to see a wall at a radius r1, at a distance r1 and at an angle alpha 1 with respect to its own reference frame. It will tell. So, robot will be having a reference frame. So, using the reference frame, you can say I am seeing a wall at r1 alpha 1, I am seeing a wall at r2 alpha 2 and I am seeing a wall at r3 alpha 3. I mean, that is the way how the wall can actually be characterized. You have distance and an orientation, at what orientation robot is seeing. So, that is what you can see. So, that is basically the ZT, which is the observations of the robots. So, you have the ZT. Now, we have the map already given to the robot, and the robot actually check with the map. Okay, so this is the map, and map has got a coordinate reference frame here, and the map has got all the information. From this reference frame, you have a wall here at 1 r and alpha, you have another wall here, you have another wall here. All these informations are there in the map. But you cannot really compare this one and this one, because all these measurements are with respect to the reference, the robot frame. So, what the robot will do, will actually convert look at the position where the robot is currently and see from that position what are the images it is supposed to see, what are the objects it is supposed to see, and that is basically the ZT hat. Okay. So, ZT we have I is equal to 1, 2, 3 in this case, okay, and then there are many things the robot is supposed to see if it is at this position. Okay. If it is exactly at this position, it should have actually seen this also, or this also, like this also. I mean, there can be many things which the robot will be able to see if it is exactly some location. So, we will look that one and then try to predict what are the things that the robot is seeing. Okay. So, that is the ZT measurement, and then the observation usually consists of a set of single observations extracted from the different sensor signals, okay, like features like lines, doors, any kind of things. Okay. So, we will put that as sensor. So, these are the robot will be able to see from the sensor. Okay. These are all shown in the sensor frame. Okay. So, either you need to change everything into the world frame, or you can change everything into the sensor frame. Any one of these can be done, and this transformation we call this as the transformation H. Okay. So, the measurement prediction have to be transformed to the sensor frame. So, you have prediction based on the map. So, that all will be converted to the sensor frame using the transformation H. Okay. So, how do we do this? So, now this is what actually the robot is seeing using the sensor, and then it will actually extract the lines. So, these are the lines that will be extracting using some image processing algorithms. It will actually identify the edges, and then each one of these will be mapped to Rj alpha j. So, it will be Zti will be alpha I Ri. So, you can can be any number of numbers can be there, and we assume that the sensor has got some kind of a covariance sigma alpha alpha and sigma RR. That means there is a error in the measurement of alpha and R. So, there can be some kind of an uncertainty in the measurement also, that is the sensor covariance R. So, you will be having multiple observation. I can be many things because there are many lines. So, all these can actually be mapped to a model space. We can see there can be 1, 2, 3, 4 measurements. So, alpha j, Rj. So, there will be 4 things the robot the sensor is actually seeing. 4 objects or 4 features are identified with its parameters Rj, alpha j, are these 4. So, that is the observation example. It is all from this location, it is able to identify the get the features. So, that is the observation. Now, the next one is the measurement prediction. Prediction is ZT hat. Okay, so as I mentioned, it will check from the map, and then based on the map, it will try to find out the predicted observations if the robot is at that location. So, this is something which the algorithm will try to do. If the position is given, of the robot position is given, it will try to find out what are the features that near to that, and then say that okay, these features are supposed to be seen by the robot. Okay, and since we transfer them to the sensor frame, we use the transformation Hj and then get all these Zt hat j. Okay, so there will be predicted observations. Okay, this Hj is mainly the coordinate transformation between the world frame and the sensor frame. That is the Hj. So, in this particular case, you will see that this is the world frame. W is the world frame. So, you have this world frame, and the features are given like this. Okay, each one of these features can be given as like this. Now, we convert that into the sensor frame and then see what are the features of the robot is supposed to see. And you will see that all those lines which the sensor actually saw are there, but in addition it says that this wall also supposed to see by the robot. If it was actually in this location, it should have been seeing this wall also. So, that is what actually you can see here. So, there is a feature here also. So, 1, 2, 3, 4, 5 features the robot is supposed to see, but it is seeing only 4 features by using the sensor. Now, we will try to match each one of these features and then try to see corresponding to this what is the robot actually seeing, corresponding to this is there anything seen, like that we will check each one of these. Okay. So, that is the stage where we try to do the matching. Okay. So, the prediction basically all these will be converted to the robot frame, and there will be a transformation matrix Hj which can be given like this. Okay. Because you have alpha and theta, alpha is with respect to the world frame and theta is with respect to the robot frame, and therefore, this alpha t minus theta, theta is the orientation of the robot. So, alpha t minus theta will be the orientation difference between the world frame and the sensor frame. Similarly, the position will be Rt minus xt cos alpha plus Yt sin alpha. So, if you see the difference, the position difference, Rt is the distance of the feature from the reference frame or the world frame, and x is the position of the robot xt yt. So, we will try to find out the difference between the actual r and then xt cos alpha and yt sin alpha. That will give you the variation from the world frame to the sensor frame. So, this is basically the transformation matrix which transforms the images from the world frame to the robot frame. And you can get its Jacobian also. You can take the partial derivative of this with respect to alpha and r. You will be getting the Jacobian, which will be obtained like this. Oh, sorry, partial derivative of this with respect to x, y, theta. You will be getting this as the Jacobian. So, this H, capital H, the Jacobian will be this one for alpha sin alpha 0, 0, minus 1 cos alpha sin alpha will be the Jacobian of the transformation. So, you have this Jacobian obtained. Now, we look at this. Okay, this is the observation, the green one is the observation, and this is the measurement. Now, what the robot has to do is to match each one. Okay, so it will check the first one, it will take j is equal to 1 and I is equal to 1 here, and see what is the difference between this one and this one. Similarly, it will check what is the difference between this one and this one and this one and this one. Similarly, all these. So, you will see that if it is measuring or finding out the difference, that is Zt minus Zt hat, this first one, this one and this one, the difference will be very small, but the difference between all other measurement prediction will be very large. So, if it is smaller than a particular value, then only it will be considering that these are the same. Okay. So, if the difference between this one and this one is smaller than a particular value that is decided by the programmer, then we will say that okay, what we are seeing and what it is observed are the same, what it is supposed to see and what it is seeing are the same. Then we say that okay, these two are matching and the others are not matching with this. Similarly, we will take the next one and then say find out which one is the matching one, and the difference is smaller than a particular value, then say that okay, these two are the matching ones. So, we will say that this one and this one are matching. Like that we will take, and we will say that okay, this one there is nothing to match, so we will discard it. Now, for each one of these matched one, we will try to find out what is the VIT, that is what is the innovation between all these matched one. That is the innovation that we get for only for the matched one, and for the matched one we take the H also, or we will find out the transformation, the Jacobian H corresponding to those matched images. So, that is what we do. So, we can see here this is the world coordinate frame, and this R, and here this is alpha, and the theta is the orientation of the robot, and W alpha is the orientation of the feature with respect to world frame, and R alpha is the orientation of the feature with respect to the robot frame. So, we will be able to get that H, the transformation matrix, and then we will be getting the innovation VIT also for the matched features. Okay, so as I mentioned, the VIT will be the difference, and this is the H, that is the this is the H, which is the transformation matrix in this case. Okay, so the validity of the correspondence between the measurement and prediction can be evaluated through something called the Mahalanobis distance. So, basically Mahalanobis distance is a small value which is defined. So, we will see that okay, if the difference is smaller than this, then we take it as a matching feature. If it is more than that, we say that okay, they are not matching. So, we cannot really take the difference between those two, and we will using that Mahalanobis distance, we will try to find out all the innovations. Okay, and once we got the innovation, we will try to find out the innovation covariance using this relationship Hj Pt Hj plus Rt, where R is the sensor covariance, and Pt is the covariance at the current position, and H is the Jacobian of the transformation matrix. So, we get the sigma innovation covariance. Okay, so now, so as I mentioned, there is no match between these, and there is a match between these two, this one, and this one. So, we just look at what are the features matched. So, only the matched one will be used for calculation of innovation. So, we know that these two are matching, though there is a difference between the R and alpha in both cases. So, that is basically tells that the position of the robot is not the same as what actually it is supposed to be. And for each one of these, we will try to find out the innovation. And as you can see here, so you will see that this is the position of the robot, and as per the robot position, it will take the measurement, it will see the features. So, that these are the features it is see. But as per the map, it was supposed to be like this, the robot was supposed to be like this. If there is a real actual position of the robot is here, it should have actually seen it in this format, okay, or in this position and orientation. So, that is the difference. So, there is a difference between what the robot is seeing and what the robot is supposed to see. So, we will take that information for correcting the position of the robots. Okay, so, we get this Kalman filter gain using the information sigma innovation and Pt and Ht, and then update the robot's position using Xt is equal to Xt hat plus Kt Vt, where K is the Kalman gain and Vt is the innovation, the difference between observed and actual one. And the covariance associated with this Pt minus Kt sigma innovation Kt transpose, where K is the Kalman gain. So, we know Kalman gain can be obtained from the covariance and the sigma innovation. And once you have this, we will be able to calculate the new Xt, which is the position of the predicted or the estimated position after the observation will be Xt, which will be Xt hat plus Kt Vt. So, as I mentioned, it will be the previous position after the prediction plus a gain multiplied by Vt, that is the difference between the observation and the prediction. So, you will be getting the covariance here. So, covariance and the position. So, that is what we needed. So, we want to get the Xt and Pt at the new location. So, now this is how it will be finally. So, you can see that the prediction of robot position was using the magenta. So, prediction is basically what the robot predicted using its odometry. So, that is the prediction here. Then the measurements actually showed that okay, if this was the what the robot is seeing, but supposed to see, and the robot position is somewhere here. So, that green one is the position and its covariance also you can see. So, you can see the magenta, the ellipse with magenta color is very large, and then the prediction one also, the green one, it again shows it is a large green circle ellipse. And now, when you fuse these two, we are actually getting the new position as the red one. So, the red one is the new position and the red ellipse is the new uncertainty. So, you can see from this position, it was initially here, once it moved and used only the prediction, then there was a large uncertainty which represented by the magenta ellipse. And then when we use the sensors, it actually predicted something, saying that okay, it is seeing something different from the what is actually the robot is seeing not correct. What as per the map, it should have been somewhere here, and the robot position should have been here. And now we fuse these two information, then we will get a new estimate which actually says that the robot position is somewhere in between these two, and its uncertainty is now reduced, which is shown by the red ellipse, which says that the uncertainty has come down drastically. So, this is the step that the robot will be taking at every movement, every step as the robot moves, it will calculate using the odometry, and then it will update it using the sensor, and again it will move and again keep on doing this. So, this is why the robot needs to have bit of computation as it has to move. So, it has to observe, then it has to identify the edges or identify the features, do the matching, and then recalculate its position and correct its position, and then it move forward. So, that is why robots are a bit slow, because it has to do a lot of computation as it has to move. It is not just like you command the robot to move and then robot keeps moving. It has to recalculate its position, and then only it will be able to get a direct and desired path for it to move. So, that is the basic principle of Kalman filter based localization. I hope you understood this. Okay, so these two methods, that is the we discussed about two methods for localization. So, the Kalman filter was the method where actually we do the localization if we know the previous position and its covariance. And this assumption in this both the methods were that we know the map, and there is a map available for the robot to check or the robot to verify its position, or cross check with what it is seeing. But in many cases, the robot will not be having the map of an environment, especially when the robot is going to an unknown area. There is no map available to the robots. So, in that case, in such cases, the robot needs to do a localization. At the same time, it has to do the map building also. So, it has to build the map and then localize itself in that map. So, this is basically known as autonomous map building and then localizing itself. So, you need to do both map building and localization. Okay. So, this is basically the simultaneous localization and mapping. So, once the map is known, it can do the localization using the Kalman filter or other methods. But when the map is not there, it won't be able to use the method. So, we need to go for a simultaneous localization and mapping method, which is known as the SLAM, which is again a very well known and a popular terminology in robotics field. So, it is a process by which a mobile robot can build a map of an environment and at the same time use this map to reduce its location. So, it has to build the map and then use the map to reduce its location. So, both the trajectory of the platform and the location of the landmarks are estimated online without the need for any a priori knowledge of location. So, it does not need to have an a priori knowledge of location, because the robot will be using the information collected using sensors to create the map and at the same time localize it. So, this is basically known as the SLAM. Just to explain how it works, so then we will look into the mathematical formulation. So the basic principle is that the robot starts with a known position. Assume that the position is known, the initial position and uncertainty is known. Then it starts with a location, and then it looks around and then sees something. Suppose the robot is seeing an object M0, it will actually create an information, it will create a database. Okay, I am seeing an object at a distance of R0 and alpha 0, something like that. It will create a map from its current location. So the current location is known, so it will know that okay, from this location I am seeing an object which is R0 alpha 0. And there is an uncertainty because the robot position is uncertain and the sensor used is uncertain. I mean, it has got uncertainties, errors. So there will be an error in the object position also. So that also will be recorded. How much will be the error that in the position of the object? And the robot starts moving further. And as it moves, its uncertainty increases. Its position uncertainty increases because it's only having the odometry. So at every odometric calculation, the uncertainty increases. So the robot is very much uncertain about its position. So that is why it's a large ellipse. And again, it will be seeing some objects. So it will actually see two objects. In this case, okay, any objects, number of objects. So it will record it as M1, M2. It will say, okay, I am seeing an R1 alpha 1, R2 alpha 2. But from my current position, this is my current position. Based on this position, it calculated what is the current position. And from that position, it is seeing two objects. And it has got uncertainty because the position is uncertain and the sensor uncertainty is there. Therefore, there will be large uncertainty in the object also, okay, the position of the object. And it keeps on doing this, it keeps moving around, and then as it reaches here, its uncertainty is very huge because it has traveled all the distance. So it has become highly uncertain about its position. But then from this position, it sees the same object M0. Okay, so now we have two observations for the same object, from one from this position and one from this position, and there will be a difference, or then it can calculate if it is from here, what should have been the position of the object if it is in this, the robot is in this position, because it's already there in the map. This object is already there in the map, and now the robot can actually use that information to recalculate its position using some kind of a data fusion. And once it does that, then the uncertainty will come down drastically. Then this position uncertainty will come down drastically. Now this uncertainty has come down because it has seen the same object, or the same feature it has seen, and therefore since it's already there in the database, the robot will be able to use that information, fuse these two information, and then recalculate its position. Similar to the Kalman filter localization we saw, it will be able to recalculate. And once it recalculates this position, it will back calculate and find out what is the uncertainty in this also. So similarly, it will be able to recalculate this position. Like this, the robot keeps on moving, and if it moves further from here, it will see something here. It will recalculate this position and record the position of the object, new object, based on the information. And after going through this many times, the robot will be having a much more clarity on all the objects in the arena. So it will be creating a much better map, and then it will be able to localize itself using the fusion method or some algorithms that we already use for localization. So this is the basic principle of SLAM. That is only to explain what is the logic of using the SLAM algorithm for getting the map and localization. So this way, the robot will be able to identify or create a map of the environment, and then say that okay, within this map I am in this position. So that is the localization. So this is possible for the robot to do. So that is the basic principle of simultaneous localization and mapping. So to go to the mathematical formulation of SLAM, so we can actually say that xt will be the path of the robot. I mean, you can actually say it's a set of points. The points will be, and xt will be having its own space. So that it will be having like x, y, and theta will be the parameters. At every t, it will be finding out what is the new position. That is basically the robot path. And then you have the control input ut, which is the motion robot motion control input, similar to the previous case we discussed. And then we have a M, which is the map of the environment, the map which is being created by the robot, which is the M, and ZT is the observation what the robot is seeing in the sensor frame. So, the SLAM problem is to recover the model map M and path X from odometry and observations. So, we have only odometry and observations. So, using this we try to create the map and get the path X. So, when you say create the map, that we are actually making the map, and get the path X means we are trying to find out the location of the robot. So, the SLAM problem is basically recovering the model map and robot path from observations. Okay, so the online SLAM is basically getting the current position of the robot using the map information, current information and the control inputs. Okay, that is basically known as the online SLAM problem. Offline SLAM, you need to have the complete path identified at every point, it has to be updated. Okay, so now we will see how can we use this Kalman filter for SLAM. So, we call this an extended Kalman filter, because in Kalman filter earlier we discussed, we were just looking at the position of the robot and its covariance, I mean the covariance. But in this case we need to have an extended state vector which actually talks about the positions as well as the features in the environment. So, we have many features which can be given as M0, M1, etc. So, we have an extended state vector in this case, which are the features of the Mi are the features in the map. So, we do the same procedure what we did earlier. We go for the prediction and then using the measurement model observation we create the state vector. I mean this vector will be updated. At every stage it will be updated, and then whenever there is a matching between the features observed, we use the Kalman filter and then update the position xt, and this xt will be all the previous positions also will be extended. So, the state vector will be updated whenever there is a matching observation. So, that is basically the estimation. So, this way you will be able to use the Kalman filter principle in order to get the SLAM done. Okay, there are many methods to do the SLAM. So, one is the extended Kalman filter SLAM. There are many other methods also. So, this one I already explained. So, if you go through this, you will see that the extended vector you will be having. So, as I mentioned, every stage it will try to find out the vector. So, you will be having a large vector. So, initially you will be having an x0, y0, theta 0, and then you will see that an alpha 1, r1, and then it will be x1, y1, theta 1, then you will be having an alpha 2, r2, alpha 3, r3. So, every stage you will be having these vectors, these parameters to be updated. So, you will be having a state vector which will be having the dimension depending on the space and the number of images. So, this vector will be kept on updating, and after many travels like this, as you can see the robot keeps moving, you will see that this vector kept on updating, and at some stage you will see that there is no more updating happens. Then it says that okay, that is the correct map of the environment and the correct position of the robot. So, this is the way how the extended Kalman filter will be used for localization and mapping. So, this shows an example. So, suppose you leave the robot in this kind of a area. I mean this is the there is a building or some arena where the robot is allowed to move freely. So, the robot will start moving and then collect the information, and because of the error there will be a lot of uncertainty in the beginning, and as you can see the robot position and the map will be completely in a disarray, and after some time the robot will be able to get much more clarity because it will be able to seeing the same objects again and again. So, it keeps on updating the state vector, and finally the robot will be able to get a clear map of the environment, and then the robot will be able to know its position where it is in that particular map. So, it will be able to do the simultaneous localization and mapping. So, that is the basic philosophy of SLAM. Okay, this is basically just to introduce the SLAM concept to you. Of course, you need to, if you are interested more, you can actually refer to a lot of literature. There are a lot of literature available in SLAM. If you just search for SLAM, you will see hundreds of papers on various SLAM strategies. So you can go through it, and then, or you can go for some advanced courses. You will be able to learn more about SLAM. Okay, so with that, let me conclude the discussion on localization and mapping. So we talked about the localization problem and what are the various challenges in localizing a robot in known or unknown environment. And then we talked about the primary method of odometry and how the odometry can be used for localization. Also, we talked about the error models. So how the error propagation happens, and then how we can use the error propagation to predict the errors in the position of the robot, or when we do the localization using odometry, how can we predict the errors. Then we talked about the probabilistic or map based localization, where we follow a 5-step process to improve the localization accuracy by using the perception update. It's not only the prediction update, we use the perception update also to get the localization done. And we talked about 2 methods, Markov and Kalman filter based localization, and briefly talked about the map building and SLAM, and then how EKFs can be used for SLAM applications. So these are the things that we discussed in the last few lectures. I hope you understood the basic philosophy of localization and mapping and the challenges. And as I mentioned, if you are interested further to know about this particular area, you need to go through the literature and then try to implement some of these concepts in the real field. You will be an expert in localization. Okay, so I will stop here. Next class onwards, I will talk about path planning of mobile robots. Thank you very much.